Up until now, we've been considering the functions that you can get by starting with variables and numbers and combining them using sums, products, quotients, and differences. So we can write down, functions like f of x equals x squared plus x divided by x plus 1 to the 10th power plus x, all of this minus 1 over x. But there's more things in heaven and earth than are dreamt of in your rational functions. For instance, can you imagine a function f which is its own derivative? I'm looking for a function so that if I differentiate it, I get back itself. Now, if you're thinking cleverly, you might be able to cook up such a function very quickly. What if f is just the zero function? Well, if I differentiate the zero function, it's differentiating a constant function, that's zero. So this would be an example of a function with its own derivative. But that's not a very exciting example. So let's try to think of a non-zero function which is its own derivative. How might we try to find such a function? So to make this concrete, I'm looking for a function f. So if I differentiate it, I get back itself. And just make sure that it's not the zero function. Let's have this function output 1 if I plug in 0. Now, how could I rig this function to have the correct derivative at 0? If the derivative of this function is itself, the derivative of this function at 0 should also be 1. Can you think of a function whose value at 0 is 1 and whose derivative at 0 is 1? Yes, here's a function, f of x equals 1 plus x. This function's value at 0 is 1, and this function's derivative at 0 is also 1. But if the derivative of f is f, then the derivative of f is also the derivative of f, which is also f. So the second derivative must be f as well. So if this function is its own derivative, the second derivative of f would also be equal to f. Now, specifically at the point 0, that means the second derivative of the function at the point 0 would be the function's value at 0, which would be equal to 1. Now, is this function's second derivative at 0 equal to 1? No. If I differentiate this function twice, I just get the 0 function. But I can fix this at least at the point 0. If I add on x squared over 2, now this function's derivative at 0 is 1, and this function's second derivative at 0 is 1. Since f is its own derivative, the third derivative of f must also be f. No worries. If the third derivative of f is also equal to f, which is a consequence of the derivative of f being equal to f, that means the third derivative of f at 0 is equal to 1, but this thing's third derivative is just 0. But if I add on x cubed over 6, now if I take the third derivative of this function and plug in 0, I get out 1. The fourth derivative of f must also be f. Okay, yeah, I got to deal with the fourth derivative. I'm out of space here, but no worries, I'll just get more paper. Here I've written down a function whose value at 0 is 1, whose derivative at 0 is 1, whose second derivative at 0 is 1, whose third derivative at 0 is 1, whose fourth derivative at 0 is 1. And you can see this is sort of building me closer and closer to a function which is its own derivative. If I try to differentiate this function, what do I get? Well, the derivative of 1 is 0, but the derivative of x is 1. And the derivative of x squared over 2 is x. And the derivative of x cubed over 6, well, that's x squared over 2. And the derivative of x to the 4th over 24, well, that's x cubed over 6. And yeah, I mean, this function isn't its own derivative, but things are looking better and better. But the fifth derivative of f must also be equal to f. Okay, yeah, the fifth derivative. I'll just add on another term, x to the 5th over 120, and if you take the fifth derivative now of this function, its value at 0 is 1. I've written down a function so that if I take its fifth derivative at 0, I get 1. The sixth derivative of f must be equal to f. The sixth derivative, I'm out of room, but here we go. Here is a polynomial whose value, first, second, third, fourth, fifth, and sixth derivative at the point 0 are all 1. And you can see how this is edging us a little bit closer still to a function which is its own derivative. Because if I differentiate this function, yeah, the 1 goes away, but the x gives me the 1 back. And the x squared over 2, when I differentiate that, gives me the x. X cubed over 6, when I differentiate that, gives me x squared over 2. X to the 4th over 24, when I differentiate that, gives me x cubed over 6. X to the 5th over 120, when I differentiate that, it gives me x to the 4th over 24. x to the 6th over 720. When I differentiate that, I've got x to the 5th over 120. And now, of course, these aren't the same, but I'm doing better. The 7th derivative must be equal to f. To get the 7th derivative at 0 to be correct, I'll add on x to the 7th over 5,040. The 8th derivative, I'll add on x to the 8th over 40,320. The 9th derivative, I'll add on x to the 9th over 362,880. Okay, this isn't working out. We're not really succeeding in writing down a function which is its own derivative. Let's introduce a new friend, the number e, to help us. Here's how we're going to get to the number e. This limit, the limit of 2 to the h minus 1 over h as h approaches 0, is about 0.69, a little bit more. On the other hand, this limit, the limit of 3 to the h minus 1 over h as h approaches 0, is a little bit more than 1. It's about 1.099. Now, if you think of this as a function that depends not on 2 or 3, you could define a function g of x, right? The limit as h approaches 0 of x to the h minus 1 over h. In that case, this first statement, the statement about the limit of 2 to the h minus 1 over h, that's really saying that g of 2 is a bit less than 1. And this statement over here, if you think of this as a function g, this statement is really saying that g of 3 is a bit more than 1. Now, if you're also willing to concede that this function g is continuous, which is a huge assumption to make, but let's suppose that's the case. If that's the case, I've got a continuous function, let's say, and if I plug in 2, I get a value that's a little bit less than 1, and if I plug in 3, I get a value that's a little bit more than 1. Well, by the intermediate value theorem, that would tell me there must be some input so that the output is exactly 1. I'm going to call that input e. In other words, e is the number so that the limit of e to the h minus 1 over h as h approaches 0 is equal to 1. And this number is about 2.7183 blah blah blah. Now let's consider the function f of x equals e to the x. So let's think about this function f of x equals e to the x. Now, what's the derivative of this function? Well, from the definition, that's the limit as h approaches 0 of f of x plus h minus f of x over h. Now, in this case, f is just e to the x, so this is the limit as h approaches 0 of e to the x plus h minus e to the x over h. Now, this is e to x plus h, so I can write this as e to the x times e to the h. This is the limit then, as h goes to 0, of e to the x, e to the h, minus e to the x over h. Now I've got a common factor of e to the x, so I'll pull out that common factor, and I've got the limit as h approaches 0 of e to the x times e to the h minus 1 over h. Now, as far as h is concerned, e to the x is a constant, and this is the limit of a constant times something, so I can pull that constant out. This is e to the x times the limit as h goes to 0 of e to the h minus 1 over h. But I picked the number e precisely so that this limit was equal to 1. And consequently, this is e to the x times 1. This is just e to the x. Look, I've got a function whose derivative is the same function. We've done it. We've found a function which is its own derivative. The derivative of e to the x is e to the x. E to the x is honestly different from just polynomials and rational functions. We couldn't have produced that number e without using a limit. E to the x is the function that only calculus could provide us with.